In this video, we'll examine the final two forces acting on aircraft in flight, weight and drag. First of all, weight. Now, weight is a force as opposed to mass. Think back to Newton's second law of force equals mass times acceleration. Weight in this case, our force, is equal to the mass of the aircraft multiplied by gravity, which is acting as our acceleration. Remember, g, gravity, is equal to 9.81 meters per second squared. So what we can say, therefore, is that as we increase our mass, our weight, the force, will be increased. So what's the effect of mass in aircraft upset recovery? Well, first of all, we have inertia. The increase in mass increases the inertia which we experience, and this means that we need to anticipate more in order to capture the datums that we're trying to achieve. We established that in level unaccelerated flight, lift is equal to weight. At the stall, lift is already at its maximum value, as we saw, so the only variable which can change the speed at which the stall is reached is the weight. A higher mass will lead to a higher stall speed for the same conditions, and we'll examine this in a little bit more detail when we get onto stalling and spinning. But for now, suffice to say that mass is a factor when we are considering our upset recovery. If you're flying an aeroplane with a large band of potential loadings, then you may find that it behaves quite differently when empty versus when heavily laden. Moving on, let's examine thrust. We established earlier that in unaccelerating flight, thrust must equal drag. Therefore, if we look at the power required for level flight, we'll find that it matches the drag curve. When the drag is at its minimum, the minimum drag speed, then we will also find the power required to maintain that speed is at its lowest. As we accelerate faster than the minimum drag speed, we saw an increase in the zero lift drag, and therefore we will require more thrust in order to sustain that airspeed. As we decelerate below the minimum drag speed, we saw that the lift dependent drag increases, and therefore below minimum drag speed we will again require more thrust in order to sustain a particular speed. If we now look at the power which is available to us, we'll find that it follows a curve, something like this for a jet engine. The point at which these two lines intersect is the maximum speed that we can fly in level flight. This is dictated by the maximum output of our engines and the amount of drag that the airframe is producing. As we get to the lower speed end of this graph, we're limited by the maximum amount of lift that can be produced by the wings to fly at a particularly slow airspeed in level flight. And also, as the drag increases due to the lift dependent drag, the amount of power that we have available at those low airspeeds to maintain our level flight. In our next video, we'll move on and look at the balance of forces in flight.